the place we're talking about for questions. So so in your Slack channel, you have these two private channels that have little locks next to them. So if you have a question like Hunter did, you know, it would be good to add them here. When you get, again, general is for like general questions like the one we had. Technical would be like somebody had trouble getting onto the RStudio server stuff, so that got resolved. And the main difference to separate these is the technical stuff tends to be more nitty gritty stuff that may like go on for quite a long way. And so having multiple questions in the technical channel could be a little bit more difficult. It could be difficult if we only had one channel. So, all right, so now's the time where if you would like to unmute, I'd be happy to take any suggestions or any ideas anybody had when they looked at this data. So like, what variables did you look at? Did you find anything interesting? So go ahead and unmute if you have anything to add. You could type it in general too, but you're welcome to just unmute if that's easier. If Jared's online, they are able to unmute, correctly? In this channel or in this instance that we have going?
Looks like some folks are typing some things in general, like Naj found, that's pretty interesting, a gap in the years during World War II. That would be really interesting. So I think that if people, so see how it says 5 of 9, there can be 9 people in, I'm not very familiar with Hopin, but like if there's 9 people in this part, those people can talk. And there's like the 33 people that are watching that I think includes the 9 people. I'm not entirely sure, but Naj, you're welcome to like be in this part and actually say what you did if you made a graph or if you made a summary table.
Here, I'll just do it.
If you prefer.
I always get this. I always type the names of these things wrong. You'd think by this time I'd not do that with this data. So here's how Max does development. He does something and then does it a better way minutes after. So I'll change the alpha on this to be more transparent so we can see. Oh, and the other thing I do, and don't tell my boss about this, I prefer black-white theme.
I prefer theme minimal.
I know, I don't.
That's okay. We can
still be friends. We have this gap here, right? Yeah, that's interesting. I didn't think about that. Yeah, so how could we have done that? So we could do that visually. Another thing we could have done would be aims group by year built, summarize, or actually, you know what? Even easier, count. So what count will do will give us the number of data points for year built. And then let's say year built greater than 1940 and so yeah, nothing in 43 or 44 and very little in 42. That is something I've never seen in this data. Wow, that's
really interesting, actually.
Yeah.
That's really great, Naj. I hope I'm addressing you appropriately, Naj. That's super interesting. Thank you for sharing that.
Anything else anybody would like to mention?
Kaylee just shared something very interesting.
Right. So there's no missing data. Yeah, I did. The only missing data really that, so when I made the process version of these data, there was a lot of missing data where things like there was no pool. And so I made some choices to say like, well, if there's no pool, then the square footage of the pool will be 0. And, and the quality or the, things like that, like, I don't think there's a field for, is there a pool? But what I did is I tried to translate instead of, because a lot of times we have to get rid of missing data or impute it somehow. And it's weird if you're imputing the pool size if somebody doesn't have a pool, right? So what I decided to do is just to encode them differently, the data. I did mention the electrical system. The 2 or 3 data points that for electrical that were missing, there was no discernible way to figure that out. And I should also say that this data has been scrutinized to an unbelievable degree. It was part of a Kaggle competition, and they went in full Scooby-Doo sleuth mode, where I think they were calling the assessor's office, asking them questions about houses, which is kind of weird. Because there are a couple of houses in here with very weird sale prices, and some people figured out maybe why that is. Maybe not saying it's money laundering, but some weird stuff that was going on in some of these data points. So yeah, there's no way I could figure out what the electrical situation was for that handful. So yeah, that's something I just decided to get rid of. But otherwise, there was missing data, but I just encoded it away. So yeah, hopefully that answers your question. Let's see, just summary and glance over everything, and then looked at lot frontage and noticed a lot of zeros, right? So, oops.
So lot frontage, what does that mean? That's like the
So I believe frontage would be like the in front of your house. That's okay. I'd never heard that term until I moved to New England. And so yeah, so there are some houses that have nothing. They're right on the street, like it might be an apartment building or something like that. So they have 0 and then a lot of other stuff. You'll also see that in things like pool. Oops. Pool areas the same way. There are some things with non-zero pool area, but the vast majority of them have no pool. And actually, yeah, I think that's an aspect of the binning more than anything else. So you do see, for example, if I went mean Ames dollar pool area equal to 0. Most people do not have pools, so they have 0 square footage. Yeah.
Rafter brings up a really interesting and important point for modeling about the factor, how factors are distributed.
Yes. So the example that we give, well, we're going to talk about this in a little bit, but as another example I'll use is what is the name of let me find the name of the subclass, MS subclass. So if I look at MS subclass and do a bar chart, bar, wow, that's not what we want. So let's pretty that up a little bit. First thing I'll do is do a chord flip. That way we can see the labels a little better. We can also try to reorder, but I'll just keep it here. Most everything is one story, since 1946 2 stories since 1946, and so on. Like 1 story with finished attic. Finished attic's kind of weird, or maybe not. Seems to me it is, but like there's not that many of them here. We will talk about this, and there's another one, 1.5 story PUD. Not really sure what that means. All ages. So we'll talk about this for another data in terms of modeling. There's a bunch of different ways you can handle this, and we'll talk about the effect it would have on some models and so on. But this is going to come out a few times. And it actually is part of a hands-on exercise. So there's a bunch of strategies here to deal with this, or to mitigate it as a problem. Is there anything else anybody would like to suggest? So one that I have noticed is I think a lot about distributions of data. So aims. So if you're wondering why somebody piped in the data the way that they did here, I always forget about this. If I just type in ggplot here, and I'm trying to remember what the name of the variable is, it doesn't autocomplete this way. But it turns out if you pipe a data set into ggplot, it will autocomplete. So if I say, I can't remember the name of general living area, but I remember it starts with an R, you can't autocomplete this way, and it doesn't do the same thing otherwise. So that's a nice little feature here of ggplot. So let's look at a histogram of that. It's a relatively skewed distribution. You have some houses with very large living areas, and then like there's sort of like the average house in here, and then a few that are very small. It's not really symmetric, so the rate of large houses is not the same as the rate of small living area houses. Same thing if we were to do sale price. So sale price. We see that we have some very expensive houses, some that are inexpensive, and it's somewhat right skewed. Now these aren't like make it or break it kind of characteristics of a data set. We will, when we analyze this data, we will log the sale price. There's a couple reasons for that. If we're using more statistical models, this is called a variance stabilizing transformation. And it has better statistical properties of this. By doing it that way, your errors tend to be more normal and things like that. Another really practical aspect of it is you'll never predict a negative sale price. So if you do leave it as is and don't model on, let's say on a log scale, it's possible for really inexpensive houses to say that they're, you have to pay me to buy them kind of thing, which is not hopefully true. So there's both statistical and non-statistical aspects of this that of transforming. Now, like living area, it's a great question. Like, would you want to transform that? We'll talk about this in the feature engineering chapter. For some models, I definitely would. In other models, I probably wouldn't. If you're doing in tree-based models and things like that, they tend to be more resistant to problems regarding skewness. But there are other models like partial least squares, or if we use principal component analysis, those things chase variation, and having skewness, that skewed distribution, if it thinks it's normal, but it's really skewed, these data, which aren't really outliers, they're just parts of that long tail, would have a sort of a higher influence on the data than they would, or on the model than they would otherwise. So, a lot of things in modeling, whether you should do them or not, depends on the model. So it's hard to make blanket statements. One other thing I'll mention, especially about living area, is if I plot that against sale price, and then just do a scatter plot. Oops, forgot something. What did I forget? Oh, right, equals. we have these like outliers out here. This is going to come up again. We have some houses that are pretty large, but are pretty cheap, relatively speaking. So you can see kind of a linear association here with living area, which makes a lot of sense. Note that the variance here is heterogeneous, that the variance in sale price increases with general living area. That might be a little bit of an issue for some statistical approaches. So one thing we might want to do is let's look at them both on the log 10 scale. This is probably a little bit more palatable. You see the variance has been stabilized. It doesn't fan out the way it did before. We're logging, so the y-axis here, the data points that are sort of aberrant, these three houses, these pesky three houses in this data set, are not quite as large outliers as they were before because we've logged in both dimensions. So this is an example where performance-wise, you do see a slight bit of hit in performance by not transforming general living area. But just when I eyeball the data, I much prefer this situation where general living area is on the log scale than not. It's more of a qualitative statement and something just based on experience. But having them both logged, I like this a lot more than the unlogged version. Yeah. So, and over time, general linear area is surprising. Let's look at that. So let's make that Y, and then year built, and then let's not log X. Yeah, that is interesting, right? So let's put a smooth on there, June smooth, and I'll say S equal false. Yeah, it's like up and then it's down a little bit on average, and it's up and then maybe stabilizes a little bit. Yeah, let me do you one better. This is going to come up in the notes a little bit. What if we did the same thing for sale price? Let's keep everything as is. So again, it's a little more subtle here, but we have, a higher sale price comes down over time for years and then starts to increase again over time. There might be another factor affecting it here. We'll talk about that a little bit in the notes. But again, this is really good because basically when we get to the feature engineering bit, a lot of the things that we might do to our data are based on these types of questions. So we might look at the data and be like, oh, that's weird. What's that about? And is that related to anything else in the data? And that would inform us in terms of like what model terms to include and so on. You'll see in some of the notes, some of the notes, like what I'll do is like, I'll find data points that just don't seem to do well and then start trying to reverse engineer why that is, like what's different about those data, and so on. And that usually ends up having me like insert a new term or something into the model that captures that like subpopulation that's just different than others. And so
I think based on some questions here, can you clarify what year the sale prices are in? So the year built, like the houses are of all different ages, but what are the years are the sale prices from?
Yeah, that's a great question. So the question was like, are they priced for inflation? No, my belief is that the sale price is the most recent sale price. So like if you Google most addresses, you'll get their sale history. And I think what they did in this data set is let's say there's a house in here that's been sold 5 times since it existed. The sale price is the last price when it was sold. So it's possible we have some houses that were sold 30 years ago and are being compared to houses that were sold like, 3 years ago. So that's a little bit of an apples and oranges kind of thing. Yeah. Nobody's ever brought that up. That's a very good question. Theoretically, the assessor's office would have assessments on these things that are probably more modern and those have their own issues about like why are they assessed like that. but these things were not all sold at the same time. And then we'll do one more. Let's see, Patrick has sizable dip in construction in the 80s. Right, that is a great question. I don't know. As much as I've looked at these data, one thing I did is last year with an intern that we wanted to update this data set. And I found that there's almost no other houses that have been sold since this data set was assembled, at least according to the assessor's office. I didn't scrape it, but we did everything we could to find new data for this data set and could not find any. So it makes me feel like there's some factors in here, like maybe there are economic factors, maybe there are other factors. It could be, like, for example, I don't know if it's true, but if we think about what defines Ames, it could be that there are other houses being sold. They're just like over here and not exactly in Ames. And not anything about Ames. This is not a pejorative statement, but I've been to Ames, and I'll be honest with you, I've been on Lincoln Highway, right here, and it's all corn, just to be honest with you. So it's very interesting, at least when I was there. As soon as you deviate outside of the Ames proper, it is all fields. So I suspect that maybe that might be a limiting factor, that people might make more off of having fields that they continually grow crops on than they would real estate, and so on. So I don't know. I was in Australia giving a talk and using these data, and Diane Cook was there, who lived in Ames for many years. And honestly, she would be the person I would ask these questions to, because she was there for so long. Yeah. So one other thing that is going to come up in the notes that I wanted to illustrate while we're here is looking at this neighborhood that is Iowa Department of Transportation and Railroad, which is an intriguing name. It's a neighborhood that runs east to west. And most of it's over here, near this park. And then we have some data over in a little cluster here and here. And then we have this property, and then 2 here, and then this one. And so from an east to west standpoint, we do have some outliers here. This will also come up in some of our analysis that, I'm not sure that, I don't remember, and I'm not from there, but, these are pretty far apart. This data point is part of the same neighborhood as this data point. And if you look at it, that range is half the range of of Ames. So these data points that are outlying here, geographically outlying, are going to come up in a few different analyses as we go. So actually, what I normally do when I teach is I kind of leave this tab open, because there are going to be some things that's a weird plot. Why is that the way it is? And then come back and look at this plot again. That might be a little more enlightening. So, all right, that was good. In credit to people in the workshop, there are 3 things here that we never really talked about or addressed in that data set. So we learned some things. It's good. All right. So one little sort of not theoretical aspect, but something just to think about is the modeling process versus the model. So a lot of times when we read books on modeling, they present a data set, and then they give you a model, and they give you the variables around that model. And maybe some of them are squared or logged or so on. And then they give you the model that works the best. And that is really interesting from a learning about model standpoint. It's not really how life is, though. So it's reductive in a lot of ways, where I think a lot of times when you see things in publications or in books, you're seeing the finished product. Because, they may not be interested in demonstrating the process that got there. They want to talk to you about well, here's how random forest works or whatever. But if you're doing data analysis for a living, that's not really how things work, or typically our problems aren't that easy. So we want to talk about the process of building a model. And so typically, you have like a finite amount of data. Like back in the day when I was in graduate school, somebody would show up to your office with like a hard drive or something, like a disk, and be like, hey, can you analyze this? And that was the data, right? It's like, it's this much data and that's how much it is. There's things that you do with the data. So like you think about things like, well, I'm going to fit a linear regression, so I need to think my slopes and intercepts, right? So that'd be like estimating model parameters. We'll talk about tuning parameters in a little bit, which are parameters that you can't really estimate from the data, but are important. There's things like model selection, where you might have two linear regressions with different variables and need to compare them. So that's like a within model comparison. And then there's things like, well, I ran linear regression and also ran k-nearest neighbors. Which one of those is better? And that's like between model type comparisons. And then there's things like, well, what's my root mean squared error? What's the area of the RC curve? So we need to estimate performance. And so these are just examples of some things that we would do during the process of modeling. So it's not like a finished product. And this graph that we have from one of our books is sort of like a schematic of like how my mind thinks about modeling. So what we did a few minutes ago with AIMS is commonly called exploratory data analysis, or EDA. Basically, you're just like graphing stuff and looking at counts and things like that and trying to discover things in the data. So when you get a new data set, or at least when I get a new data set, I go through a couple of phases of like exploratory analysis and quantitative analysis. So I'll do a bunch of ggplots and say like, oh, that's weird. And then I might do some quantitative analysis. It's like, well, let's compute, like, say, the sale price by neighborhood. Is that very different across neighborhoods? And so you're just investigating the data, either visually or by making summary tables and things like that. And then point C there on the graph is when you do sort of like feature engineering, which is kind of a fancy term for like, how do I encode my data? So if you think about location of a house in AIMS, there's a bunch of different ways you can express that. You can express that as like it's on the street. You can express it as longitude and latitude, which we have in this data set. Neighborhood, which we see we have that data that may not be all that great sometimes. You might think of things that are related to location that are potentially important for modeling. So a lot of times when people go house shopping, let's say people, they might be having kids in the future, they might be really thinking about what schools are there. So you might think about like location relative to certain schools, like what school district is it in? And so you have this like one underlying property, that's location, but you can encode it in one or more ways to put it in the model. In which ways you encode it really depends on the problem, and it depends on the data and the model, right? So, but the process of figuring out like, well, what data should be in the model and how should it be sort of like represented is this feature engineering. So how do we put these things together to be proper in the model? And then this little like striped region here is part D, where like we might, hopefully what we're going to do is try out a bunch of different models. We don't, for a new data set, we don't necessarily know offhand whether like random forest is going to be great or linear regression or so on. And I have a lot of instances in the past where something simple like logistic regression beats the pants off of like a boosted tree or random forest. It's very difficult to know ahead of time what's going to be best. So you're probably going to want to try various models on the same data set and see which ones seem to be working better. We're going to also talk about this thing called model tuning, where we're going to have to like optimize this model over some parameters. And that's where the stripes come in, or even for like model number one, there's going to be variations of model number one that we're going to fit to see within model what's the best way to fit it, and so on. So you go through this like little phase of like initial modeling, and then that phase will tell you probably like, oh, wow, like linear regression really tanked on there. I'm going to have to really work on that if I want to try that. But trees did really well. So maybe let's like focus on trees instead, and so on. So the outcome of this stage D here is whittling down models that seem like they have promise and others that don't. And how do you do that? Well, you're probably going to look at some performance statistics. You're going to look at what was the R squared or the accuracy. So you're doing like more quantitative analysis. And then like for regression problems, you might plot the residuals and be like, whoa, why is, I mentioned these 3 houses in Ames that have really low sale prices. Those would be ones that are hard to predict, and that would come out in your post-modeling exploratory data analysis. And then based on that, you might say like, oh, right, they're next to the airport, or, that's not the answer for those, but like whatever it is that you think is important to put in the model to represent that thing it was lacking before is like another phase of feature engineering. And then, you just keep doing this and doing it until you've gotten to the point where things are good enough, right? They're like, they fit whatever the goal is of their application. And sometimes, that goal might be low. It might be like, we want to predict this, but it doesn't have to be perfect. In other cases, it very nearly has to be perfect to be useful. So there's some level of expectation in terms of performance of your model, where you basically get it down to like 1 or 2 models that you're really like, oh, geez, like these seem to be really good, and I like them both, but I really need to pick one. And so like the very last thing is usually like a bake-off, and that's when we talk about a test set. This is where your test set comes in. And if you've never heard that term, we'll talk about it in a little bit. But this is like, we're going to predict the test set for our models, pick the one that we like the most, and do this very, very, very last model fit, which is like the finalization of the whole process. And that's the model you would use going forward to make predictions. So yeah. So the comment in the general channel is like, oh, I feel a lot better about life looking at this. This is the reality of things. Some data sets are campaigns. Some data sets are so difficult that you're literally pulling your hair out trying to make it work. I can probably say I've only had like 2 or 3 situations in my entire career where there ended up being like one thing that was sufficient to give you really good prediction performance. Right before I left my last job, they were having a manufacturing problem and had a lot of images of the materials before they went out. And it was like literally the simplest image analysis you could have done gave you nearly perfect accuracy to detect the defects as they happened. And I felt really good. And I'll be honest with you, I made it seem like I cured cancer. It was literally something that could have been done in Excel, but I had to be honest, I made it sound like whew, that was crazy, but I figured it out, sort of thing. So yeah. All right. So one other thing I want people to think about is how we're using our data. We typically think about it like we have some data we're going to use for analysis. We're going to have some list of variables. We're going to put those in the model. We're going to specify a model, and that's this bit here. And then we're going to fit that model using the data. Again, this is really reductive, and it's not typically, you compare this to this, right? This is the reality of things. This is that previous graph with nothing in between. Like, we have the data, it's all configured correctly, we have the right variables, we fit in the model, and we profit, kind of thing. We want to make sure that we spend our data well. I've been trying to think about how to talk about this in a way that is like an analogy. If we use all of our data for the model fitting, then we don't really have any data used for like an independent data set used for performance estimation. And so the way I've been thinking about talking about it is, we always need a set of data that can tell us if we've made the wrong opinion or we've made the wrong choices. If we only have one data set, it's very easy to overfit to that data set. And so we always need another data set that's like a second opinion. Tell me if I did something wrong. And so, I just wanted to mention that here. We'll talk about data usage a bit in this. And this is quite different, again, from when I was taught data analysis. And there's also, if you've never heard of this term, the garden of forking paths, or p-hacking, it doesn't have to be necessarily nefarious, but I think a lot of times people think of this final fitted model and they don't talk about all the choices, data-driven choices even, that they use to get to that model. So our models are really a function of all the choices we made along the way to get there. And it's important to keep that in mind. So the classic case of this is, if you've ever heard of stepwise regression, like you'd have a linear regression with like 50 variables, and then SAS and other things had like this button where you could push that said like, do a bunch of like statistical analysis to tell me what things should be in the model. And they basically use p-values to make these choices, which is a really, really flawed approach to doing it. And so there's this idea that the models that came out of the stepwise procedures, that those standard errors in those models were correct. And they're really not, because they ignore all the things that came before them. So all the decisions that went into that final model somehow need to be factored in. And we'll be able to do that to some extent with the methodology we'll talk about a little bit later. This is going to come up again, in other words. So one thing we want to do is we want to define like a data analysis process. So we have data and variables that come in, and we have this like box that defines all the modeling and pre-processing things that happen to the data in the model. And then the outcome of that is some fitted model object, right? So if I'm talking about doing stepwise or some sort of like variable selection, that would be inside this box. Or if we need to do imputation or a data transformation, or again, like feature selection and things like that, before the model fit, those things are all significant steps that affect the model, and they should be considered part of the modeling process. So the point I want to make here is, and this is going to come up later, that if we exclude some of these things from the modeling process and think like, well, imputation is just something we do to the data and it is what it is, it doesn't have any effect on the data, that's probably not true. And if you think about it that way, it's possible to get performance estimates that are very flawed and optimistic. So what we're going to do is talk about something called a workflow later, which encapsulates everything from the feature engineering bits and transformations and filters all the way through the model, and even maybe post-processing things you might do with the model. And those are going to fit into this box that we'll then resample and do things with. And we have a data structure called a workflow that is good at combining all these things together. So you'll see this more too. Some little naming conventions when we create objects. Something that's a model is going to be like a model specification, which is like, you'll see in a little bit, it's basically like, we're going to fit a linear regression. We haven't estimated anything. We haven't said what variables. Like a model specification would be like, hey, we're going to do linear regression versus random forest versus a support vector machine. It's more a description of what the model is. So when we create those objects, they'll have the suffix of underbar mod. When we take a model specification, we fit it, like estimate things, we'll call that underbar fit. There are these things called recipes and workflows we'll talk about. And so those will be underbar rec and underbar WFL. When we do model tuning, the results of that will be underbar tune. And then sometimes we'll just have a generic thing that's like results. So we'll call that res. So we will stick to this convention in the notes. So hopefully we'll be able to look at an object and say, oh yeah, that's a recipe or a workflow. Yeah. So then lastly, like if you want to learn more about any of these things, there's things like if you want to learn more about the tidyverse, like there's tidyverse.org and R for Data Science. Jay Bryant has a fantastic per tutorial and things like that. So we would recommend these things. The one I'll specifically call out, because we've done a tremendous amount of work on it this year, is we have tidymodels.org. And so if you just type that in, you get here. And we've spent a lot of time sort of like optimizing this website to help people learn about tidymodels. So there's a page on the packages and what they all do, and so on. Probably the best thing here is the getting started pages. So what we've done is we've sort of take the sequences of things that you would do with modeling, and each one of these is like an extended vignette on like, how do we build a model? So they're set up to like be actual examples that you can run. Things like, why does it work that way? So we're trying to answer common questions that people have. The nice thing about this is we just added this. If you've ever used RStudio Cloud, you can click on these buttons and it opens RStudio.cloud in sort of a preloaded environment where you have everything set up to run through this particular tutorial. So you could do this locally and copy and paste. But if you're like really new to R and new to tidy models, you may not have like, the resources or things like that that you might want. So we have like some buttons here that will open this up in RStudio Cloud and make it really, really easy to learn. So these are like things about like, here's how we do it in tidy models, but also here's the things to think about in data analysis. And then there's a little case study at the end. The learn section here has some categories. So, if you're doing more statistical analysis type stuff, we have some really excellent tutorials. Like here's a nice, where's that? A nice little GIF about how K-means works that Allison Horst put together for her stuff. So we've spent a lot of time on this. I think it looks really good. And there's a lot of really, really good materials in here. One thing that I'm particularly happy about, and I use quite a bit, is if you come up to this magnifying glass, Tidy Models has a lot of packages in it and a lot of things, a lot of functions. And so what we did is we created a little like search routine that if you were like, right, there's that function Tidy Models, I don't remember what it was called. There's so many Tidy Models packages, like what do I do here? So, you might say, oh, right, it's some Bayesian stuff. So you can type in Bayes and get in a list of all the things related to Bayesian analysis that are in tidy models. So same thing with the types, all the models we have in recipes. There's a lot of code and functions that do these things. And so if you ever have trouble finding anything, and these sometimes would include things, for example, that we did not make. So model time is a time series package. It works with tidy models, and somebody else made that package. But it has parsnip models in it. So we include those things here, and then we link out to all the help pages here. So, we took a lot of time to do this. We wanted to have as helpful documentation as we could come up with. And so tidymodels.org is sort of the culmination of that. So this is good. We also have a book that we're writing that I keep saying this time frame, and I don't think I've been accurate at all. We want to get like the first, I don't know, like 7 or 8 chapters out pretty soon. We're just like wordsmithing them right now. So there's also an open book that we're going to be writing, or have been writing, that'll get linked here in other places. It won't be hidden anywhere. But between that and tidymodels.org, we have a lot of like crafted resources to learn more about this. So, right. So that's the end of the introduction. Any other questions that people have? Okay. We have an hour left, and I've been talking a lot. It's hard to tell if we need a bio break because we should do like a Slack poll maybe. But if you want to take we have an hour left. If you want to take a 15-minute break, we could do that. Or what people want to do.
Jared says you have two. We have 2 hours left. Yeah, it's still.
Okay, sorry.
Yeah,
I got all night. No, just kidding. Okay, so somebody said, yeah, that would be great. So why don't we do this? It's my clock says 3:06. Why don't we come back in 15 minutes? So let's say like around 20 after 3. I can wake my dog up so she'll stop snoring in the background, and we will continue then. I'll turn my video and audio off, but again, anything that pops into your brain in their intermediate time, just post that in general, and then we will answer it when we come back. Okay, so about 3:20ish, we'll start up again.